All right, this lesson we are going to talk about the damped guitar string, right? Last time we did an expression for the undamped guitar string, which resulted in a very clean, very simple wave equation that looked like UTT equals C squared UXX. And here I'm using a notation that's a little more compact than we used in the previous demonstration, right? So UTT is the second partial derivative of U with respect to time. UXX is the second partial derivative of U with respect to space. U is always understood as a function of the distance from the nut, and that's what X is, and the time after the pick release, that's what T is. The distance from the nut, the time after pick release, but we're going to suppress that because we just understand that U is that formula, that function that has those two pieces in it. And we also remember that C was the propagation speed of the wave along the guitar string. And that was great, and it works really well. And one of the reasons it works well is because the damping of the string is relatively slow compared to how rockers pick, right? Rockers will pick routinely quarter notes at 120 beats per minute, and as we said, that's 10 oscillations. So we're going to try to get a sense of how damping would affect the physics of a guitar string if you just sort of let it go and you went for maximum sustain on your guitar, right? What would you get? So the way we implement damping is we add a term to the wave equation. We add a term that is almost always written as gamma partial U partial T, which would be minus gamma UT in the more compact notation. And what this is saying is that there is a force that opposes motion that has a certain strength that we characterize by a number gamma. And we'll have to learn how to interpret what this number means as we do our work. So we'll keep an eye on that to understand how do we figure out what gamma is. Because in the end, we're almost doing an engineering calculation here, right? It's couched in the terms of physics, but this is almost an engineering calculation because we're looking for numbers relevant to a guitar string. Like, you know, I think in the last physics of rock we used power slinky strings. So we're going to try to figure that out. We're going to try to really figure out what gamma actually is for a guitar string. But this tells us that this force opposes the motion. So remember how our design was, right? We started with the nut, right? And then the string had some shape that we were able to calculate. And then over here is the bridge, right? So the guitar string, at every point on that string, right, like say there's a point right here, that point is either moving up or it's moving down. We've already assumed that this point is not moving left or right, which, by the way, not an absolute guarantee, right? This is called transverse, right? It's moving only in the transverse, T-R-A-N, trans, V-E-R-S-E, right? Transverse, I guess another E. It's got only transverse motion, which would be transverse to the string. But, you know, you can imagine that this point might have a little bit of wobble left and right, right? But that is a very, very subtle effect, right? It's very, very subtle that would happen, but it could. And there are people out there who have modeled guitar strings where that effect is possible. At that point, you kind of have to abandon solving differential equations, right? Writing it down in the form of a straight up clean differential equation like this and solving for an answer, that suddenly becomes harder to do. And to get these transverse expressions in there, what you have to kind of do is you have to think of, and when I say you have to, one way of doing it, as I should say, is you think of the guitar string as a lot of points, and the points are connected by springs, right? And so you have masses connected by springs. And when you do that, and you model how that structure ultimately moves, now these masses can engage in longitudinal vibrations as well. But we're not doing that, right? So we're still assuming that there's only transverse motion, right? But the point is the thing to understand here is that this transverse motion, which is up and down, you want to think of it as you're moving through some kind of medium, right? This string is vibrating. Well, in the guitar strings case, this is the air, right? So you would say, well, maybe the air, you've got to push your way through the air, which means that the air is exerting a little force against your motion, right? So as you, the point on the guitar string, right? As you're the point on the guitar string, and you're moving this way, the air is going to be pushing back, giving you a force, right? This is a force coming back. The black, this is supposed to be your speed, right? Right. That the black vector is the speed, and the red vector is a force. And the force opposes your speed because you're pushing through a medium. That's the idea here that's captured by this term in the partial differential equation, right? So by adding that term, we've now really changed the nature of the partial differential equation. We have to solve it all over again. And that's what we're going to do. So let's begin. So to begin the solution of the damped wave equation, we use the exact same process that we used for the undamped equation, which is the separation of variables. And we presume that the dependence on space and dependence on time live in two different functions, and that the final answer is the product of these two different separated functions. And by taking this guy and substituting it into here, we can generate two ordinary differential equations. And those ordinary, well, first of all, the straight substitution is going to look like this. X times the second time derivative of t is going to equal the speed of propagation squared times the second space derivative of x times t minus gamma x times the first space, or the first time derivative of t. And now we say, hey, is it possible to get all the time on one side and all the space dependence on another? All the time dependence on one side and all the space dependence on another. Now, there is an interesting question of what differential equations, what do the properties of a differential equation have to be such that it is separable? Not all partial differential equations are separable. This ability to use this technique is limited. And we're not going to go into why or when or what the conditions are, but understand that this is a technique that applies for the ones we're going to talk about, but does not apply universally, right? So the next step is to do this separation. And let's see, I get 1 over c squared times this second time derivative divided by the overall time function, plus gamma over c squared times the first time derivative over the overall function. And then that's the left side, and then the right side is the second space derivative over x, right? And here we have done it. We have actually separated all of the time dependence on this side and all of the space dependence on this side. And what that means, and I'll run through this again, but what that means is that this particular combination of time derivatives and the function t, all of the time dependence must disappear here. Because as time moves on, if this changed, this can't change when time moves on, but this equality is always going to be true. Ergo, the time dependence must go away, and likewise the space dependence must go away. And so they must both end up equaling a constant. And we could call that constant lambda. Now, if we call the constant lambda, that would be the instinctively natural thing to do. It's a constant, it's a number, we don't know what the number is, let's just call the number lambda and push on. But we kind of know how this whole thing is going to turn out. We're going to turn these things into ordinary differential equations, right? That's our goal. So if we kept lambda in there in this form, what would happen? Well, first of all, we can separate the two equations, right? That's the important part, right? I can now take this equation and I can move it over here, and that's a totally legit equation, and then I can set this equal to lambda, and now I have two ordinary differential equations. Now notice this was a partial differential equation, a PDE, and a partial differential equation, that's almost all of physics is driven by partial differential equations. Ordinary differential equations are much easier to handle. They're all in one variable. And so now we have two ordinary differential equations. And And these two ordinary differential equations, the notation kind of becomes, I don't want to use the word superfluous too many times, but I don't want to say redundant either. But let's look at it this way. The notation T, 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 that's supposed to mean, this 3 equals means it's defined as. This isn't a profound statement. This is a statement about symbols, right? This is the second derivative of t with respect to time. But t was only a function of time all along, right? So there was never any alternative, right? And because of that, these partials really had to be regular differentials, which are commonly in calculus indicated by d. I needed to square there. But up here with u, right, u is actually, u is known to be a function of x and t. So when we specify its derivative here, we are talking about the partial derivative of u, right, with respect to x. So the notation there is legit. But once you do this, you have to understand that these are just ordinary derivatives, not partial derivatives. And, you know, there's another school of notational thought where you go, where you can say that t is, t is actually, you write it with 2 dots on top, and x is written with primes. So, but we're going to stick with the subscript notation. All right, now with this, we will focus on this guy first, which we've already solved. We've already done this one, right? We have solved long ago. Oh, this is a little too thin. I want to make this a little thicker pen. We've already solved this guy a long time ago, and you know, this differential equation becomes x minus lambda x equals 0. And this is where we say, hey, look, we know how to solve ordinary differential equations. We've seen second order linear ordinary differential equation. You know, to use all of the sort of library of information we have, it sure would be nice if this looked like x minus lambda squared, plus lambda squared x equals 0. That we can solve by literal inspection. And we have the right to do that because if we just make the separation constant minus lambda squared, right, instead of lambda, it's an arbitrary number, right? So we are forcing it to be negative, but if lambda turns out to be imaginary, then that thing can be positive, right? So we don't really lose anything by defining it as minus lambda squared, but we get the benefit of having our partial differential equation look like the easy form we're used to seeing. And the same is true for t, right? If you blow up the differential equation for t, you get t, let's see, plus gamma t first derivative plus, what do you get? You get c squared lambda squared t equals 0, right? And that's, again, an ODE that we know how to solve. It's not as trivial as this one. Like, this is like the first ODE you learn, right? This one is like the second ODE you learn. But we do know that we can solve that almost by inspection. And so it's much nicer to choose lambda early on to be minus lambda squared. All right, so these are our 2 differential equations that we have to solve. The first one we know the answer to, right? We've already solved it. I'll do it in blue, but it is going to be a times the sine of lambda x plus b times the cosine of lambda x, right? We remember that there's no difference from last time, and in fact, the boundary conditions are going to come in, and we're going to discover that with the boundary conditions, we're going to be able to discover that lambda has got to be n pi over L. We'll do that in a moment. But then with the other one, t, this one suddenly is different, right? This one we will, using the elementary theory of differential equations, we write down its solution as a constant c times e to r1 of t plus d times e to r2 of t. And r1 and r2 are these important numbers that solve the characteristic equation r squared plus gamma r plus c squared lambda squared equals 0. And what I always liked about this is like why you learn the quadratic equation in high school, right? So this is a quadratic equation, right? So we just solve for r1 and r2. There's going to be two solutions, and those two numbers are the exponents of the solution for this expression. And that's not the same as this, by the way. It's not really the same as this. And the reason is that the possibility for r1 and r2 to be imaginary is what is the key difference here. Well, not totally the possibility of r1 and r2 to be complex numbers, right? They could be fully imaginary, they could be fully real, or they could be complex numbers. And that possibility is what makes the damped solution more interesting and more accurate than the undamped solution. Anyway, what is the solution? So R1 and R2 are going to equal, and now I'm just using the quadratic equation, minus gamma over 2 plus or minus 1/2 times the square root of gamma squared minus 4c squared lambda squared, right? So there you have it. That is the two values of R1 and R2. Now, this is another place where we start cleaning up the mathematics so things are a little bit neater. And it turns out cleaning up the mathematics very frequently is not only a good idea, it actually gives us some kind of insight into what's going on. So this expression, although perfectly fine, it's a little bit unwieldy given the fact that gamma that we chose in our original differential equation, well, I guess that ends up here. But in the original differential equation, gamma was this damping term, right? And it's very important. It shows up in now this damping term, right? First of all, notice that the damping term did not show up in the spatial part, right? Lambda, if we remember how this works, lambda is going to be dependent on the boundary conditions, but gamma doesn't have an opportunity to show up anywhere. Look, only thing that shows up here is lambda. Gamma shows up in the time pot side. And what's really important is it shows up quite significantly in this time part. So, but gamma was just the number we picked for our equation. So if we decided, hey, instead of calling gamma gamma, we defined it as 2k, right? So if in our very first equation we had written utt equals c squared uxx minus 2k ut, right, instead of minus gamma ut. If we had put a 2k there, right, then what would have happened? Where would we be sitting right now? Well, we would be, let's see, I'll do it in blue. Gamma, this would be a 2k, right? This would be 4k squared, right? And so you would end up with minus k. This 2 would go inside the radical as a 1/4, right? So you would get k plus or minus the square root of k squared minus c squared lambda squared, right? So we would end up with R1 and R2 equals minus k plus or minus the square root of k squared minus c squared lambda squared, which is arguably a little bit nicer to drag around than all of what that would have been, right? With the 1/2s everywhere. Let me make sure I got that right. Just sort of checking my notes. Yeah, okay. So now we know the two solutions for the separated damped wave equation. We know this solution and we know this solution, and we know these are known numbers. R1 and R2 are known numbers. Well, I guess R1 and R2 are not yet known, right? Because if you look at the expression for R1 and R2, we still have lambda to deal with, right? But lambda is very easy. because lambda just comes from this spatial, the boundary conditions on the string. So we remember from our last lesson that when you apply the boundary conditions on the string, where you force u of 0 for all time to equal 0, and u at the nut, or at the bridge, which is L, for all time to equal 0. When you force those things to be the case, then we now know that lambda breaks up into the modes, right? There are an infinite number of possible lambdas which will satisfy those boundary conditions, and each one is some multiple of pi over the scale length, right? And this is where the modes start entering the situation. So now we know that this equation, this equation right here, there's an infinite number of versions of it that will work, each indexed by the mode, lambda. And we will write that as lambda n, and then these coefficients also become functions of n. But we also know that Bn has to be 0 from the boundary condition. So this guy goes away. This is exactly the same solution as last time. The point is we can lean on the fact that lambda sub n is still n pi over L. Now, with that in mind, this equation here, I can make this substitution, right? And I can get, let's just do it. Let's just do the whole thing out. We get c n pi over L. Wasn't it c squared? And then, well, it's everything squared, right? It's this whole thing squared, right? And then presumably we know k from the engineering of the situation, right? The viscosity or the thickness or the weight of the medium that's slowing down our string. And so now we know what R1 and R2 are, right? And what we also now know is this thing here, this square root, right? This square root is really important because there is the possibility that k squared and this term here are negative, right? Meaning, I'm sorry, not they're both negative, but the difference between them is negative, in which case that square root is imaginary, and we do have what I just said, which is an imaginary value for R1 or R2. And you know that if it is, you're going to get this, because it's a quadratic equation, you're going to get two solutions, and they're going to be complex conjugates. So with that in mind, we do have to be, we're suddenly aware of something, right? We're aware of the fact that there's different types of R2, right? There's the R2 that are imaginary. This could be a real number, in which case there's R2 being real. It can't be purely imaginary, though. That's the important part. This square root is either imaginary or it's real. But this guy's always real. So this number is always either entirely real, if this is, say, 0, or it's complex with a real and an imaginary part. Okay, so we have zeroed in on the solution. Let's sort of summarize what we got. All right, so we still know that now our solution's been broken up into modes. And the nth mode is going to be the product of the nth, we'll call them harmonic, but we really should change the word. It's not really harmonic anymore because the word harmonic literally means that it's one it's a member of the harmonic series, well, when you think of it in terms of music at least. And it's no longer going to be a member of the harmonic series, as we're going to see in a moment. This damping actually throws a big damper. See what I did there in the harmonic series. So, but we have solved for xn, right? We've solved for xn, so we know that the space part of this is going to be an sine of n pi over Lx, right? We know that's true because we knew Bn was 0 from the boundary conditions at the nut and the bridge, just like last time. And we know that t, the time part of this, right, we can write that down too. And the time part has two constants, Cn, E, and E is raised to the power, let's see if I can get this right. It's going to be raised to the power minus k plus the square root of k squared minus c squared lambda n squared, where lambda n equals n pi over L, right? And this is times time, right? So it's sort of this times time. And then you have, and I'll just write it underneath, you have dn e to the minus k minus the square root of k squared minus c squared lambda n squared times t, right? So and then there's, I guess, the closing bracket would be over here. Let me move it over a little bit. And so what you have here is this, this sum now, and the difference is this minus sign, right? The only difference between this and this is this minus sign right here. But what's interesting about this, of course, is now you can use our basic like exponent laws, right? So I can now get rid of this minus k, and let's move the e over a little bit, right? So I have e and e. I can actually get rid of this plus, because I'll leave it there just so you know it's the positive square root, right? And that minus k now actually comes out and goes all the way to the front to e to the minus k, like that. Oh, minus kt, right? And that's really, really important, because now you're looking at a solution that has a complete factor of e to the minus kt driving it in front. And it applies to the entire solution. And right away, you see how damping affects the answer, right? This is the time part of the answer, and this is the space part of the answer. This part is definitely part of the time portion of the answer, but it affects everything as a simple factor. And it means that as time gets large, right? As time gets large, this is going to be a large negative exponent for e, if k is positive, right? The presumption is that k is going to be a positive number, right? If it was a negative number, that means the fluid would be actually pushing the string along, but it's a positive number. And so this exponent will be a negative number, and that means you're going to get e to the minus large as time goes to infinity. And e to the minus large is very, very small, which means that as time goes on, the entire solution is going to get damped by this. And in a long period of time, there's going to be nothing left, right? Now, it never goes to zero, which is another weakness of our approximations. Even though it dampens, it never goes to zero, because e to the minus very large number is still not zero. It's very close to zero, but it's still technically not zero. But this is the damping, right? This damping that's where our new differential equation has really made its money. It pulls out this real part of this root, right? Remember, there was a root up here was this expression. The real part that's always present, that's the damping. And what's left behind, right? What's left behind is somehow related to the frequency of the mode's vibrations. So now we got to look at that very closely. So to do this, let's focus on this time, what's left over from the time part of the expression. I'm going to rewrite it. So here we have it. This is the time portion, just the time portion of our final solution. This is what ultimately is Tn of t, right? The nth mode of the time portion of the nth mode of our vibration. Now, the only way this can oscillate, right? The only way this can be an oscillatory solution is if these numbers here are in fact imaginary, right? So we need, for us to have an oscillating solution, we need k squared minus c squared lambda n squared, right? That has to be less than 0. And let's see, a few things we want to remember. First of all, of course, is that lambda n is equal to is n pi over the scale length, right? That's what lambda n is. So I can just replace this right away with n squared pi squared over L squared, right? That's important. And the other thing we want to remember is that the frequency of oscillation for the regular undamped case, right, it was equal to n, the harmonic number, times the speed of propagation, c, over 2 times the scale length. And if you remember, c was defined as, let's see, the square root of the tension on the string divided by the mass density. So you can kind of see how all of these expressions ultimately get traced back to their physics, right? It's the tension on the string, the mass density of the string, the scale length of the guitar, and this is just a convenient way, C is just a convenient way of writing that down, but it ends up being the speed of propagation on the guitar. K is now this new thing for damping. That's the amount of damping, and we now know that K is sort of the 1 over E limit of the damping, and so this is the criteria for oscillation. If you don't have this case, if the damping is so strong that this is not true, then that means that all of these expressions here are going to be real numbers. So this will be a real number, and that'll be a real number. And in this case, the exponent will be positive, and in this case, the exponent will be negative. The positive one would be unphysical, because then as time goes to infinity, the string would the string, this would grow with unbounded growth, and the string's displacement would grow unbounded. So Cn would have to be 0, right? That would drive Cn to be 0. And then for this one, it would decay, and it would just contribute even more to the overall suppression that is indicated by the first piece of the answer. Where'd that go? Oh, that would be even, it would contribute even more to the damping you're expecting with K all by itself, right? So if this condition isn't met, then the string will not oscillate. So we can decide, well, okay, I want to know the answer under all circumstances. I want to know the answer under the circumstance where it oscillates or it doesn't oscillate. So, or we can just say, no, let's assume that this condition is always met and only look for things that oscillate. Because in our guitar, we think all the modes oscillate, right? Or not. Well, can we figure that out by looking at this expression? And the answer is, yeah, we can, because this has to be less than 0. Well, when is it going to be less than 0? Well, without knowing the scale length that we're going to use, or knowing the tension on the string or the speed of sound, right? Without knowing these numbers, without knowing the damping, you can't really immediately decide. But we do know about this n, this harmonic number. As the harmonic number gets bigger, this gets bigger. And this never changes, right? That's just a feature of the environment. But this is always going to get bigger. So there is a point where the harmonic number is going to be so big that this will definitely be less than 0, because n grows. L is fixed, C is fixed, pi is fixed, K is fixed, but n can grow for each mode. So there is definitely a mode somewhere that does oscillate, right? It does oscillate. There's a value of n where this is going to break into negative territory, and that mode will definitely oscillate. Now the question is we want all the modes to oscillate. So we just set n equal to 1, and we write our expression as k squared minus c squared pi squared over L. And this is the condition for the fundamental mode, right? The fundamental mode to oscillate, right? If the fundamental mode oscillates, all the other ones will oscillate. So if we're going to examine the case of the guitar string, this has to be satisfied, right? Nobody has a guitar string that's being played underwater. I don't even know if that would do it. You'd probably have to be played like under viscous oil or something to make it not oscillate. So this is the condition that we're going to be experimenting with or considering. So the frequency of the vibration, if these are imaginary, if these are purely imaginary expressions, meaning this condition is true, which means this will always be true, because remember, lambda n is just this n pi over L. Then the way we write this down is we say that the frequency of the oscillation, I'll give it a little hat, because I'm going to say the frequency of the nth mode. And I'm giving it a hat to distinguish it from these frequencies, right? These are the frequencies of the undamped, right? The undamped guitar, right? And this is the frequencies of the damped guitar. Damped guitar, okay? So these frequencies are going to be, so up here in the exponent, that's called the angular frequency, right? So these frequencies are going to be the square root of k squared minus c squared, and I'll go back to lambda again, right? But it's got to be divided by 2 pi, right? Because we're dealing with angular frequencies now. So you divide that by this. I mean, this is an angular frequency, so you divide it by 2 pi. You may remember the expression. The angular frequency is over 2 pi equals the regular frequency, where regular frequency is cycles per second. Angular frequency is radians per second. Okay, so this expression for the angular frequency, what does that lead us to? So we substitute for lambda over n, right? So you end up with the square root of k squared minus c squared n squared pi squared over L squared, right, divided by 2 pi. And then you start pulling stuff out. And I think what we'll pull out is, so we're going to pull out, this, right? We're going to pull out this, because what we want ultimately is we want to know is how are the frequencies, in this case, different than in the undamped case. Well, in the undamped case, the frequency was NC over 2L. So let's pull out an NC over 2L. So we get that will equal NC over 2L, right? And that's going to be times the square root of, and then we'll have to have L squared K squared over C squared N squared pi squared, right? And then this is minus 1. And then I still have a 2 pi to deal with. See, the 2 pi will go here. I'll put it up. Wait a minute, 2 pi is down there. Oh, no. The 2 pi will go... I'll put the 2 pi here, right, over 2 pi, right? And then this is k squared, L squared, c squared minus 1. And that should be so our goal now, we're going to take this expression and we're going to simplify the inside and make it a little clearer about what's going on. What we're going to do is we're going to pull out a factor of 2 pi harmonic number speed of propagation over 2L. We're going to pull that out front, outside from under the radical out into the front here. And when we do that, we're left behind with k squared L squared over c squared N squared pi squared minus 1. And remember, this whole thing is divided by 2 pi, right? So this 2 pi down here cancels with this 2 pi up here. And then this expression here, right, that equals the old harmonic frequencies, right? So I can now write this whole thing in a very suggestive form as the new harmonic frequencies, or the new partial frequencies. I'll call them partials, overtone frequencies, or partials, to get away from the word harmonics. But it equals the harmonic frequency multiplied by this new factor, k squared L squared over c squared n squared pi squared minus 1, right? And that is our big deal. So we've already learned, we haven't even solved, the full equation, right? We've just found these terms, we're looking at the time part, right? The time part of the solution for a single mode. And that time part is right over here. And just by looking at this time part, saying, hey, we want it to oscillate, so we know this has to be imaginary, and that establishes some kind of criteria to be imaginary for all the modes, right? K squared has to be greater than this, than c squared pi squared over L squared. But once we do that, we'd say, okay, well, now what's the frequency of the oscillation? Well, the frequency of the oscillation is this number, which is an angular frequency, right? So that's going to be omega n, right? An angular frequency. And we're used to regular frequencies in hertz, so we have to divide omega n by 2 pi. So the regular frequency is the angular frequency divided by 2 pi. And then we crunch that number a little bit, and what we discover is that the regular frequency, the vibration of the partial, the overtones, or the harmonics, in scare quotes, is the same as the old harmonic, the true harmonic frequency, multiplied by this factor. And so now we can study, what is this factor telling us? Well, let's clean up the factor so we can understand all of its parts. So this was n squared and pi squared here, and this is the number 1, right? So first of all, we know that this factor is, it gets smaller. Well, let's see. As n gets larger, for the larger harmonics, this term here gets smaller and smaller and smaller, right? So as the harmonics go up, this term goes to 0, and this whole thing becomes the square root. This tends towards the square root of -1, which is I, which means that for the highest harmonics, the frequency of oscillation in the damped case approaches I times the frequency of oscillation in the undamped case. Now, we're just assuming this is a real number. We're defining this to be a real number. So this frequency has got to be imaginary, right? Otherwise this thing doesn't oscillate. But that's what it turns out to be. So the damping does not affect the frequency of the very high harmonics. The very high harmonics seem to vibrate just like they would have in the undamped case. And no matter how much damping there is, there's always vibrating harmonics. There's always harmonics where you will end up with this being imaginary. And on top of that, you will always find that the highest harmonics just ignore this damping. And they're vibrating at such a high frequency, right, that the viscous fluid just doesn't have time to interact with them very much. However, for the lower harmonics, this number can actually be significant, right? And we'll try to figure out how significant it actually is for the guitar. But this number here, when n equals 1, right, if we set n equals to 1, then that goes away. And this is our condition. This is equivalent to our condition that we talked about earlier, which was, what is the condition that allows this thing to oscillate at all? And that was this condition right here, right? Another way of saying it is this guy has to be less than 0, which is effectively the same thing. So, but this number here, based on our condition, is going to be as large as possible. So that's going to be, when n equals 1, this term here is as large as it can possibly be, because none of the other numbers change. C never changes, pi never changes, k never changes, and L never changes. So this is as large as it can possibly be, which means it's going to have the largest effect on the inharmonicity, the deviation from the harmonic frequency. Okay, good. So let's wrap this up. I mean, this is the big point, right? But let's wrap this up and get a global look at what our solution actually looks like. All right, so this now is the summary of where we are for each mode, right? This is the nth mode. This is the equation about how that mode moves. And it's the big distinction between last time is we're now kind of playing with these exponential functions, which is a little bit of a mess because we've got this imaginary feature in there, this imaginary exponent, and that's there to make sure that they oscillate. And what we've done is we've found the new frequencies of oscillation, and what we're going to do is we're going to swap the order of around the subtraction sign here to force this to be a real number. The square root will always be, the argument of the square root will always be positive, and the square root will always be real, and we compensate for that by putting in an I in the exponent. So that is our signal that this is an oscillating solution, because it's not unreasonable to just say that the frequency itself is real. So we have these two parts of the time-dependent section, that's the Tn, and then the space part is exactly the same as it's ever been, right? In fact, if we set t equals to 0 here, right, we get Cn plus Dn, right? We get some combination there, and that would combine with the An, and then you would have a single undetermined constant. The damping constant is also 1. When t equals 0, this is 1, this is 1, this is 1. So everything just is a massive constant. And you use the Fourier process to calculate what that constant is. And there's no difference, right? So the Fourier coefficients that we're going to have in the end here are going to be the same. So it's very similar. It really is just coming down to this guy. Now what we're going to do is when we look at this term, we're going to leave the exponential world because we don't like this imaginary number so much, and we're going to convert this into trigonometric functions using the standard definitions that the cosine of x equals e to the I x plus e to the minus I x over 2, and something similar for the sine, right? The sine, I think, there's a minus sign here, and there's an I down there for the sine, right? We're going to use those two facts, and we are going to convert these exponentials into trigonometric functions in the following way. And the upshot of that is this expression right here, where this the e to the positive power and the e to the negative power are replaced by cosine and sine. En and Fn are related to Cn and Dn. We usually don't even bother going through it because we haven't determined what Cn and Dn are, so the relationship of Cn, Dn to En and Fn is not relevant, but if I recall correctly, En is actually Cn plus Dn over 2, and Fn is Cn minus Dn over 2, right? That's the connection between these coefficients and those. So now we need to find out what these En, En, and Fn's are. And the way we do that is with our initial conditions. And the same initial conditions apply to this situation, right? Well, first of all, we know that the total sum, or the total answer that we're after, is going to be the sum of each of the individual modes, partials. You know, it's really hard not to call them harmonics, right? But we will. So I'll just say harmonics because we're thinking musically, and the musicians, they don't quibble over this. They'll say there's a lot of inharmonicity with the harmonics, right? And what they're really supposed to say is, I guess, the partial overtones are don't match the harmonic series or something wacky technical. But we know that we're dealing with this sum, right? And this sum here, this guy is actually xn tn, right? So we know that u of x and 0 is our initial condition, and we've solved that problem already. But let's hold off on it because what we're also interested in is that the first derivative with time at the initial, for all points on the string at t equals 0, that equals 0, right? So we need that initial condition. Last time immediately eliminated the sine term, right? It eliminated the sine term, but in this case it's not going to. And the reason it's not going to is when you take this time derivative, right? When you take this first time derivative, this beast up front contributes. It's a product rule. And what ends up happening is you end up not with setting En or Fn to 0, but setting a certain combination of the two equaling 0. So let's have a quick look at that. So with this guy in mind, we're going to take the time derivative of this thing. So the first thing is we understand that this part here has no dependence on t, so it just sort of hangs out like a constant. So we're not going to focus on that guy. We're going to focus on this part, right? And we treat this part as a product of a function times t times a product of a function times t. And we do that twice, right? So we're going to use the product rule. And that's sort of what breaks the beauty of the analysis, right? It's no longer clean because of that product rule. So when I execute the product rule on this, let's just break down one part of it, right? We'll write down e to the minus k minus kt times en cosine 2 pi I fn hat t, right? That if I just took the derivative of this guy, we immediately get minus k e to the minus kt, right? That times en cosine 2 pi I fn hat t plus e to the minus kt times the derivative of this mess, right? So the derivative is going to, first of all, it's minus sign, so it's minus en 2 pi I fn hat times sine of wait a minute, there's no I in there. That's the whole point, right? There's no I in there. Sorry, guys, there should be no I. Did I put an I over here? Yeah, there's no I in this, right? See, the idea is the I is up here, but when you do the combination, you lose the I. So there's no I in there. So let me get rid of that I. I don't know how I missed that, but 2 pi and 2 pi, right? There's no I there. And likewise, there's no I here, and there's no I there, right? 2 pi and 2 pi, like that. And so likewise, there's no I there, 2 pi, and there's no I there, and it certainly doesn't come out, right? Because it wasn't there to begin with, so it's not going to come out. So 2 pi. So okay, so sine of 2 pi fn hat of t, right? Now that's just one part of it, right? Damn, this is a little too big. Let me select this and move it. Oops. Hold on. Let me take this and move it here. Right, so that's the two pieces of just the derivative of this part. And likewise, you get a similar thing for the sine piece. And that turns out to be, let's see, I should do it, let me just do it offline. And so when you execute the product rule with the sine, you basically get other terms that just pop in like this. So we're popping in the fn sine 2 pi fn t and the fn 2 pi fn. There's two fn's floating around. So fn 2 pi fn hat cosine 2 pi fn t. And this expression, right, this expression here, this total sum, this guy here plus this guy here, that equals the time derivative. So the time derivative of un of x and t. And now you can look at this and you can say, okay, we know that the time derivative, the string starts from rest. So this guy has to equal 0 when t equals 0. And so we look at that and say, well, when t equals 0, this term is 0, right? And when t equals 0, this term is 0. But these other terms are actually still there, but they're equal to 1. So this term here equals 1, and this term here equals 1, leaving only behind en and fn to pi. When t equals 0, this guy equals 1, but you end up with a minus k still, right? You end up with a minus k in that part. So when the upshot, when all this is done, what we end up having is minus k times the e component, or the e undetermined variable, times 2 pi times capital Fn times the frequency, that equals 0. And this is now the result of the initial condition on the velocity. The initial condition on the velocity. Phew. So, so at least this seems like we have two undetermined variables, but we don't, because you pick one and the other's fixed, right? Because everything else is fixed. You know the harmonic number and the physics of the string, you get f. And if you knew f, capital Fn, or if you knew capital En, you would immediately get at capital Fn. So this relationship does, in fact, eliminate one unknown variable. It just doesn't do so as cleanly as it did in our last work. Okay, so this expression we derived from the fact that the string was motionless at the beginning of our analysis. We still have the fact that the string at the beginning of our analysis has a very specific shape. And you may remember the shape we like to use was this plucked guitar string shape, not drawn to scale, where the pick is located right there. It starts from this nice rest position, which is what we just used to derive this expression. And we remember from last time that we did this Fourier analysis on this problem, and we ended up figuring out what those coefficients were. But we do know that when ux equals 0, we know what the expression for the answer is in the damped case. All right, so now this being our solution for a given mode of our final answer, right? This is the full solution for the nth mode. If we plug in t equals 0, this part here, right, this time part, it becomes 1, right? We plugged in t equals 0 right here, and this cosine part became 1. T equals 0 right here means this part becomes 0, and this ultimately becomes En times the sine of n pi over L of x. Now now this means that the full solution, which is going to be this at the time t equals 0, the full solution at x0 is going to be the sum from n equals 1 to infinity of En sine n pi L x. And this is this, we know how to get En for this. We did it in our last exercise with the undamped string. It's interesting, the shapes of the modes in the damped case are unchanged. They're the same shapes as before. And we know what En is in that case. In fact, let me write it down. So we know that this is the solution for our initial condition guitar string. So that's what En is. And using that and this expression, I can calculate Fn. First, using the expression we derived from the fact that the string was motionless is really a relationship between Fn and En, and that relationship is the value of Fn is proportional to En, and the proportionality factor is k over 2 pi Fn. But notice this proportionality factor is not constant for every harmonic. It is different for every harmonic, and because this is not constant for every harmonic, the frequency of vibration. So this is a subtle relationship, but regardless, all we have to do is take this and multiply by k times 2 pi over Fn, over the frequency, the harmonic frequency or the partial frequency, and we get an expression for Fn. And I'll write that down now. And this is our final answer for Fn, right? it's the same as En, but you've got this factor right here. And notice the damping appears in the Fn. The damping appears there. So now, if we go back, we know that this being our answer for the overall problem, we know that En is our old Fourier components. Fn we just calculated, so now we know this, and given the physics of the guitar, we know little f, so we have our final equation. So I will write down a version of the final equation, and let's do that on the next screen. And this is our final answer, right? This is the final expression. It's an infinite sum. It's got a lot of things that are similar to the undamped string. For example, these coefficients are the same. But the thing that's dissimilar is it still has this sign piece in the time dependence, which is an interesting problem. And the frequency, Fn hat, equals the old frequency, Fn, times the square root of 1 minus, and let's see if we can remember what that was. Where did I write it down before? I think I wrote it down back here. KL over Cn pi squared, right? KL over Cn pi squared, right? So these definitions all together produce our final answer. What can we learn from this is, first of all, notice that this damping constant, K, pops out in front of everything. All the modes are summed to the right of the big sigma, and they all dampen equally, which is fascinating. But their oscillation frequency has now shifted, so the damping is not benign to the oscillation frequency. So now we have to sort of ask ourselves, how significant is that? And then what else do we learn? Well, otherwise, it's very similar. We have assumed, by the way, that all the modes oscillate, right? If we didn't assume that, if we had not assumed that all the modes oscillate, we would have had to break this sum into two parts. The first part would have been from 1 through each of the non-oscillating modes, and these cosines and sines would have been hyperbolic cosines and sines, and they would not have exhibited oscillations. Then we would have had another sum going from the first oscillating mode to infinity that would have looked exactly like this. So we would have split it up into two parts. So that is the solution for the damped wave equation. We've discovered inharmonicity, and we've discovered that all the modes dampen equally. Both of those things, the inharmonicity is definitely true. There's a lot of things that make the guitar string inharmonious, even more that make the piano inharmonious. So we have more to say about inharmonicity. The fact that all the modes dampen at the same rate, that's a little sketch. And but they definitely dampen. The question is would they all, in the real world, dampen at the same rate? And the answer is probably not quite. Okay, so that completes this tutorial on the damped